Welcome to the deep dive. Okay, so I want you to picture a massive digital landscape.
Right.
You've got thousands of servers, maybe millions of users, or even a network of sensors spread out over a whole continent
And they're all trying to talk and update data at the same time.
at the exact same time. And the one thing, the absolute foundation that keeps that whole system from just, crashing into chaos is consistency.
That's right. I mean, if two different operations try to make a critical change simultaneously and they don't somehow acknowledge each other,
It all falls apart.
the system becomes inconsistent and trust is just, well, it's instantly lost. This is really the central challenge of distributed computing.
And to solve this, engineers don't rely on luck. They rely on math. And for this deep dive, we're going into the world of quorum systems and a particularly elegant version called cyclic quorum systems, or CQS.
Right. These are basically specialized mathematical structures designed to guarantee that consistency.
So what is a quorum system fundamentally?
Fundamentally, it's a collection of subsets of participants. We call these subsets quorums.
Oh,
And the golden rule is simple, but it's really powerful. Any two quorums you pick from the collection must have at least one member in common. They have to overlap.
that overlap is the secret handshake.
Exactly.
So if one operation needs, say, quorum A to run, and another one needs quorum B, that required overlap forces them to interact.
Right, at that shared entity. So they have to acknowledge each other, process their changes one after the other, and that maintains the integrity of the data.
And our mission today is to look at the really cutting edge stuff here. We're comparing two, radically different computational philosophies that are used to find the most efficient version of these systems.
We're talking about finding the optimal starting point, the seed for these structures. And the two approaches are, on one hand, systematic, rigorous logic.
And on the other, learned adaptive intuition, the kind powered by deep reinforcement learning.
A true clash of styles.
Okay, let's unpack this, because we aren't just looking for any quorum system. We're looking for the mathematically perfect ones.
Exactly. Engineers want systems that are not just consistent, but also fair and minimally expensive to operate. So we look for three key properties in, like an ideal quorum system.
Okay, property one, fairness in size.
That's what we call equal work. Every single quorum should be exactly the same size.
Because if quorum A has 5 members and quorum B has 20,
The cost and the latency of running an operation using B is just so much higher, it's inefficient.
makes sense. Okay, property two, fairness in load.
That one's equal responsibility. It means every single entity in this system, every server, every sensor should be included in the same number of quorums overall.
So you don't want one poor server bearing the brunt of all the work just because it's, the popular node.
Precisely. You spread the load evenly.
And the third property. This one feels like the most critical for massive real-world systems. Minimal size.
Oh, absolutely. Minimal size dictates efficiency. The size of your quorum directly correlates to your communication cost.
The more members, the more messages you have to send across the network.
Right, so you want that quorum to be as small as is mathematically possible while still holding everything together.
And the mathematical frontier for how small we can actually get in a system with n entities
Yeah.
it's surprisingly beautiful.
It really is. The size of the quorum has to be at least proportional to the square root of n, or as we'd say, O of the square root of n.
So achieving that minimal size, that O of root n, while also enforcing equal work and equal responsibility, that's the holy grail.
It is, and that's exactly what the cyclic quorum system, the CQS, is designed for.
This is where that elegance I mentioned comes in. Instead of having to painstakingly design n different quorums,
Which would be a nightmare.
CQS generates the entire highly symmetric system cyclically, and it does it from a single element.
The base quorum, or the seed we talked about earlier.
So how does that work? How do you get a whole system from one seed?
It's all based on modular arithmetic. So if your base quorum is, let's call it B0, to get the second quorum, B1, you just take every number in B0 and add 1, modulo n.
So you just wrap around if you hit the
You
end.
just wrap around. To get B sub I, you add I modulo n. It's pure, beautiful math that automatically spins out n quorums, and they're all guaranteed to be the same size.
So the whole ridiculously complex design problem, it just boils down to a number theory problem.
Exactly. The entire challenge is just selecting the right initial set of numbers for that base quorum for B0.
What makes a set of numbers right?
Well, we're searching for what's known mathematically as a relaxed cyclic difference set.
Okay, that sounds dense.
It does, but it just means the base set needs to satisfy a specific geometric guarantee. Think of it like this. If your system has, say, n equals 10 sites, There are 9 possible distances or differences between any two sites, 1 through 9.
Right. The distance from site 1 to site 4 is 3. The distance from site 9 back around to site 2 is also 3, if you're doing it modulo 10.
Exactly. So we need to find a small set of seed numbers so that every single possible difference in the system is covered by at least one pair of numbers within the seed set itself.
So if I pick, say, the numbers 1 and 4 for my seed, I've just covered the difference of 3, but I still need to cover 1, 2, 4, 5, and all the others.
Precisely. The search is for the smallest possible set that covers that whole range of differences. And that guaranteed coverage is the mathematical proof that any two quorums, which are just shifted versions of that seed, will definitely overlap.
Okay, let's ground this. We had an example for n equals 8.
Right. For N8, a known optimal base quorum is B0 equals, it says 0, 1, 2, 4. It has a size D of 4.
And a size of 4 is, wait, the square root of 8 is a little less than 3, so you round up.
No.
That's not quite right.
You're close. The bound is approximately root n. For small n, it's a bit more complex, but 4 is known to be the optimal size here.
Okay, so it hits that minimal size goal.
It does. And if you
Right.
look at the differences between the numbers in that seed set,
So 4 minus 0 is 4, 2 minus 1 is 1, 4 minus 1 is 3.
you find that they cover every single difference from 1 to 7. Because that coverage is perfect, the system it generates has that perfect symmetry we want.
All 8 quorums have a size of 4, so that's equal work.
And every site, 0 through 7, appears in exactly 4 quorums. That's equal responsibility. It's an incredibly efficient mathematical machine.
If we connect this to the bigger picture, finding these optimal seeds has massive practical implications, right? It's not just about database updates.
Oh, absolutely. The real world payoff is huge. This isn't just an abstract math problem.
So where does this obscure math actually pay the rent?
It's basically anywhere you need efficient resource sharing or parallelism. So in general, distributed computing, for instance, CQS structures are used to optimize something called distributed all pairs algorithms. These are really computationally heavy tasks where every piece of data needs to interact with every other piece.
Right.
By structuring the work using a CQS, you ensure that you distribute the workload perfectly evenly, and you also minimize the memory footprint needed for all those interactions.
We also see this showing up at the literal edge of the network, right? In wireless sensor networks.
Yeah, and in that world, batteries are everything. Power consumption is the name of the game.
So how does CQS help there?
There's a variant called CQS pair, and it helps manage what's called heterogeneous wake-up scheduling.
Okay.
Essentially, it defines optimal groups of sensors that can wake up together to transmit data. Because that quorum intersection property guarantees they can connect, the sensors don't have to be listening all the time.
They can sleep more.
They can sleep more. They use the CQS structure to define these optimal staggered wake-up schedules, which massively extends the battery life of the entire network, all while maintaining guaranteed connectivity.
And then there's maybe the most impactful modern application, the one dealing with just absurd scale. And that's in deep learning.
This is a brilliant application of the theory. It's about solving the memory bottleneck in huge transformer models, the kind that run large language models.
Right, the standard self-attention mechanism in a transformer. Its memory use is proportional to the square of the sequence length, O of n squared.
Which is a killer. When n, the sequence length, gets really long, your GPU just runs out of memory. It's why processing, say, a whole book as one input is basically impossible for most models.
So how does CQS break that barrier?
There's a new scheme called CQS attention. It's a form of sequence parallelism that uses our CQS math. Instead of needing the whole sequence in memory at once,
Yeah.
the CQS structure lets the system split the massive sequence into chunks. But because the quorum property guarantees overlap in how those chunks are processed, the system still captures all the necessary global dependencies.
Without needing to load that entire massive O of n squared attention matrix into memory.
Exactly. It reduces the computational cost from quadratic to something near linear. It's a massive system-level efficiency gain.
That makes the connection crystal clear. This dense math has a really profound real-world payoff. So back to our core question. How do we find these perfect base quorums, especially when n gets huge?
Researchers took 2 very different paths here.
Let's start with the traditional approach. We're calling it the architect. It's a systematic search based on guaranteed logic.
The architect, yes, and that name fits because it relies on pure, structured logic. It's essentially a recursive search, a very sophisticated generate and test process.
Now, when I hear generate and test, I immediately think brute force, which sounds impossible for these numbers.
It would be. But the architect uses mathematical shortcuts to avoid exploring trillions of useless combinations.
How does it do that?
The technique is called pruning and backtracking. As the algorithm tries to build a partial solution, let's say it's picked three numbers for the seed so far, it immediately checks the mathematical properties of just those three numbers.
It checks to see if the differences it has covered so far even make sense.
Precisely. If that partial set already makes it mathematically impossible to cover all the remaining required differences, the algorithm knows it's a dead end.
So it just gives up on that path.
It prunes that entire branch of the search tree and backtracks instantly. That saves untold hours of computation that would have been wasted on a guaranteed failure.
Okay, I get the pruning. But I heard there was an even more ingenious optimization inspired by combinatorial objects, necklaces and bracelets.
Huh, yes. That sounds like a geometry puzzle, doesn't it? But it's a very clever way to recognize redundancy.
Redundancy how?
Imagine you find a perfect seed set, say 1, 2, 5 if you reverse it, or if you cyclically rotate it, so 2, 5, 1, or 5, 1, 2, they all represent the exact same mathematical quorum system.
Ah, so they're just equivalent solutions. They're mathematical mirror images or rotations of each other.
Right. And generating bracelets and necklaces is a classical math problem that deals with sequences that are equivalent under rotation and reversal. By building in a specific symmetry-breaking check, the algorithm avoids generating and testing sequences that are just mathematically equivalent to ones it's already found.
Which must shrink the search space enormously.
Dramatically, without losing any unique optimal solutions.
So, the architect's strength is certainty. It uses this divide and conquer strategy. You can run it across many CPU cores, and it is mathematically guaranteed to find the smallest possible solution within its search constraints, if one exists.
That's its power.
Okay, now let's pivot entirely. Let's talk about the second philosophy, deep reinforcement learning. We're calling this one the Explorer.
In the Explorer, instead of using explicit mathematical rules for pruning, it learns through experience.
Here's where it gets really interesting.
It really is. We take the exact same combinatorial search problem, finding the right numbers for that seed set, and we frame it as a strategic game.
A game played by an AI agent.
That's right.
So how does the AI know if it's winning this game?
It learns through a continuous cycle of observation, action, and reward. And there's a shared brain, which is a neural network called the policy network, that guides all its decisions.
Okay, walk us through that cycle. What does the AI agent see?
First is the observation, or the state. The AI looks at the current situation, which numbers have already been chosen for the seed, and critically, which mathematical differences are still missing. That whole picture is fed into the network.
And then it makes a move. The action.
The policy network then calculates probabilities for picking the next best number to add to the seed. But, and this is crucial, it doesn't always just pick the single highest probability option.
It introduces some randomness.
It does. It allows it to explore options that a strictly logical algorithm might just ignore completely.
And then it gets feedback.
Yeah.
The reward.
The reward signal is the key training mechanism. If the agent picks a number that successfully covers many new differences, ones that were previously uncovered, it gets a high positive reward.
So it's incentivized to make efficient, non-redundant choices.
Exactly. It learns to sniff out the best possible covering strategies over time.
And you said all of this experience goes into a shared brain.
Yes, and this is a really critical part of the design for parallel computing. You have multiple independent agents, these worker threads, running this game simultaneously. They're all exploring different pathways.
And they all report back to headquarters.
They all feed their successes, their high reward experiences back into a single centralized policy network. So they're learning collectively from this huge pool of experience, which just massively accelerates the learning curve.
So the Explorer relies entirely on an emerging strategy. It's not handed the formula for success.
Not at all.
It has to discover the mathematical properties of an optimal set purely through trial, error, and reward.
That is the core difference. The RL approach is not guaranteed to find a solution. It might get stuck or just fail to discover the optimal strategy. But if it succeeds, it has the potential to scale far more efficiently to systems where N is so huge that even the pruned systematic search would take geological time.
So when you synthesize these two philosophies, you really see a classic engineering trade-off play out.
You do. On one side, you have the architect, the recursive search. It offers mathematical certainty. You know you have the absolute best answer, and it relies on explicit, verifiable rules.
And on the other side, you have the Explorer, Reinforcement learning.
Mm.
It offers adaptive scalability. So it's trading that certainty for the potential to discover emergent solutions in these vast, untapped search spaces.
And this collaboration was stunningly effective. I mean, the systematic search for these optimal CQS solutions had previously stalled out at systems up to n equals 111
And it had been stuck there for a while.
for a long time. But by parallelizing and optimizing both of these approaches, the researchers were able to push that boundary significantly.
So what were the results?
They generated new verified optimal results for systems ranging from n equals 112 all the way up to n equals 170.
Wow.
And for the smaller numbers in that new range, it was the rigorous recursive search, the architect, that provided the guaranteed optimal solution.
But the RL approach.
The RL approach validated those results and, more importantly, demonstrated its unique ability to learn these effective covering strategies. It provides a vital complementary path for when we try to scale this to n equals 1,000 or 10,000.
So it's proof that sometimes the best way to conquer an immense combinatorial problem is by putting the rigorous logic of the architect right alongside the adaptive intuition of the Explorer AI.
Right, and the parallel implementation was key. It accelerated both the certain discovery and the strategic learning.
It really feels like the fundamental desire for efficiency, that minimal size, that equal work, is what's driving the development of these incredible tools.
It is, and the collaboration between human design logic and machine learned strategy is proving to be the most powerful combination we have for these kinds of problems.
And that leaves us with this final provocative thought for you to explore. We've seen how these mathematical structures, like CQS, translate directly into massive efficiency gains in areas like deep learning memory management. Now, if the architect uses the fixed, known rules of mathematics to guarantee optimality, how might the adaptive strategy of the Explorer AI eventually uncover optimal systems that pure architectural logic might completely miss?
Not because they're mathematically impossible.
But simply because the computational limits force the architect to stop searching too early. We leave you with that question to explore.